Hi there, this lecture is on angular momentum for algebra-based physics. This is an AP Physics 1 lecture. I am Mr. Bruce, and here we go. Today we're talking about angular momentum. Angular momentum is the quantity of an object's angular motion. It is directly analogous to linear momentum that we learned earlier this year. The equation for linear momentum was momentum equals mass times velocity. So angular momentum must therefore be the rotational equivalent of a mass times the rotational equivalent of velocity. And we call the mass the moment of inertia, the rotational inertia, and the angular velocity is the rotational velocity. Equation is L, angular momentum, equals I, moment of inertia, times omega, angular velocity. Note this looks like a W, it's not, it's the Greek letter omega. I have a ranking problem, rank the angular momentum of these three objects. We have a basketball spinning, a hoop that's rolling, this is a big hoop, and like a hula hoop sized hoop, and a bowling ball that's rolling. And it turns out if you look at the moment of inertia of each of them, the hoop has by far the largest moment of inertia. The basketball, I used a hollow sphere of 2/3 mr squared. The hoop, I used a ring of mr squared. And the bowling ball, I used a solid sphere of 2/5 mr squared. The hoop, because it has the highest moment of inertia, also has the highest angular momentum, even though it is the slowest of the three. Now, the first big idea in angular momentum is the idea that if you have a system of objects or a system of particles and there is no net external torque on the system, if all of the particles, they can be colliding with each other, but if there's nothing happening causing external torques on the system, angular momentum is conserved. This is one of the four fundamental conservation laws of the universe. All right, I have it written here for a two-object system where the angular momentum initial of the first object plus the second object equals the angular momentum final of the first object plus the second object. We can use this in a lot of different ways. We can extend it to many, many more objects, or you can, the first example is going to be the angular momentum of a single object being conserved. That object in this case is a figure skater. Initially, she's touching the ground and there's a force on her from the ground. But once she leaves the ground, that external force is gone. And there are no external forces, in fact, that are causing a torque on her. But what she does is she pulls her arms in, and that causes her moment of inertia to decrease. And therefore, if that moment of inertia decreases, but there's no net torque on her, then her angular momentum is conserved and her speed has to increase. So here we go. When she pulls her arm in, there's no net torque and angular momentum is conserved. So that means her angular momentum before she pulls them in is equal to the angular momentum after. And if you plug in the numbers, you'll see that in fact, her angular velocity must increase as a result of the decreasing rotational inertia. In the second example, we're going to be using a collision between two objects. We have a solid disk and we have a blob of clay. Now this is a collision, and it is fair to say that when the blob of clay collides with the disc experiences a torque and slows down. But also, the disc collides with the blob, and the blob experiences a torque and speeds up rotationally. But because that torque is internal, there are no external torques on this system. And the system, if you include both the disc and the blob, has no external torque, and therefore angular momentum is conserved for the whole system. So if we were to write it out, we'd say the angular momentum of the disk plus the initial angular momentum of the blob, which is 0, equals the final combined angular momentum of the disk blob system. And if you plug in numbers, you can use that to solve for the mass of the blob, which comes out to be 2.45 kilograms. So in this example, we were considering the case where there's no external torques on the system. But what if there is external torque? That means angular momentum has to change. And this is something that we saw in the last, in translation as well. We call this the impulse momentum theorem. We say if you start with a certain amount of momentum, and then there's an impulse, that will cause a new momentum to exist. So in this case, we have the initial I omega. The angular version of impulse is torque times time. So initial I omega plus torque times time equals final I omega. So here we go. We're going to apply this idea. The simple case is a ball undergoes a net torque of 11 Newton meters for 6 seconds, which causes it to accelerate. And we have to determine its moment of inertia and its average angular acceleration. Turns out these are written out of order. You have to do the acceleration first, and that's just basic kinematics. The average angular acceleration is the change in velocity divided by time, which is 7/6 radians per second squared. And then once you have that, you can determine the moment of inertia of the ball with Newton's second law. The moment of inertia of the ball is the torque of 11 Newton meters divided by alpha of 7/6, and that gives you a moment of inertia of 9.4 kilogram meter squared. This is nice because we've just figured out the moment of inertia of the ball without knowing the mass of the ball or the radius of the ball. This is a direct way to measure moment of inertia that we'll be using in the lab. We, in fact, did that in the lab yesterday. The second example is a disk rotating and it undergoes a torque, and that torque is given by a graph. And so I've taken the liberty of computing the impulse caused by the torque in each section of the graph. Remember, impulse is torque times time. And if you do an area under the graph, the torque times time is impulse. So for the first 2 seconds, the impulse is 5 Newton meter seconds. From 2 to 6, it's 4 Newton meter seconds. And from 6 to 8, it's 4 Newton meters seconds. So the final angular momentum is just given by the initial angular momentum plus the impulse. The initial angular momentum is 0.07 times 4. The impulse is 13 from the graph. So the final total angular momentum at the end of 8 seconds is 13.28 kilogram meter squared per second. The angular velocity is just the angular momentum divided by the moment of inertia. And that's 190 radians per second. Wow, that's a big speed up starting from 4. That was a big impulse. And the last question is technically answerable. The problem is, if I were to do it, I would take 2 to 3 pages because there are 3 sections of the graph where you have to figure out the displacement of each section and the velocity at 2 seconds and the velocity at the 6 seconds and plug all that in. But the worst part of it is this is in fact a changing torque, which is just like having a changing force, which causes a changing acceleration. In an algebra of base physics class, you will never see this question. The reason why is a changing acceleration means you have to integrate. You have to use calculus. And since we aren't allowed to use calculus in this class, you will never see this on a test, and you will never see this on the AP exam. So if you want to do this question fully, please take a calculus-based physics course. The final topic of the day, is going to be rotational kinetic energy. Rotational kinetic energy is the energy of a spinning object. The equation for it is just like translational kinetic energy, but instead of being 1/2 mv squared, it's 1/2 I omega squared. So the first example is a bike is rolling, and it asks, what is the rotational kinetic energy of just one of the bike wheels? So that's 1/2 I omega squared. If the bike wheel is rolling and not slipping, we can say that omega is V over R. Again, if it's not slipping, though this is usually the case with a bicycle wheel. Plugging in numbers, we come up with a rotational kinetic energy of 0.004365 joules, which is pretty small. Then it says, what is the total kinetic energy? Now, I'm not talking about the bike. I'm just talking about one of the bike wheels. And to do this, we need the rotational and the translational kinetic energy. What we're going to do first, though, is we need the wheel's mass. So we're going to assume that the wheel is a ring where I equals mr squared. So mass equals I over r squared. So the combined total kinetic energy of the wheel is the 1/2 I omega squared of the wheel plus the 1/2 mv squared of the wheel. Plugging in and substituting, we get 1/2 I omega squared of the wheel plus 1/2 I over r squared times v squared. And if we plug in for omega as well, we would notice that we have 1/2 I v over r squared plus 1/2 I over r squared v squared. And if you look at that carefully, you'll realize those two things are the exact same thing. So the total kinetic energy is actually double the rotational kinetic energy, because the rotational and the translational kinetic energy for this bicycle wheel are the same. All right, and that's interesting because that means that if you're looking at a bicycle wheel that's moving along, spinning on the ground, half of its energy is in rotational form and half of its energy is in translational form. Okay, next question. This is an interesting question because the old way to compute the speed of a marble rolling down a hill using forces and rotation is pretty involved. But if you do it with energy, you can do it very, very simply and very, very quickly. So here we go. The first thing we're going to say is that at the top, the total mechanical energy is equal to the total mechanical energy at the bottom. And at the top, it's entirely potential energy. But at the bottom, it's both translational and rotational. So at the top, we have mgh. And at the bottom, we have 1/2 mv squared and 1/2 I omega squared. And if you say that the marble is rolling without slipping, you can replace omega with v over r. And also, every single term has mass in it. So what you're left with is gh equals 7/10 v squared. Or the final velocity at the bottom is equal to 10 7ths gh. The final omega at the bottom is just that divided by r. So 1 over r root 10 7ths gh. And it's 10 7ths because it had translational kinetic energy and then 2/5 mr squared for rotational kinetic energy. The last one kind of made me laugh a little because it asks for angular acceleration. Well, you can't solve for angular acceleration using just energy. You need kinematics, which means you need time. But time is not given in the question. Energy cannot tell you anything about time on its own. So anyway, the acceleration is indeterminate without knowing time or some other piece of information that could lead you to acceleration like forces. All right, that's all I have.